Okay, all right guys, so we're going to be talking about decision trees. Let's put that on the board, that's always important, right? And we're going to be talking initially about classification. So we want to classify some new data into different varieties, for instance. So imagine we're doing some test. We have some materials, so we stick in some materials, and we have some apparatus here. Materials go in there, and out pop two features, maybe x2, let's call it, and x1. So we get, for each material that we stick in here, we get one x2 and x1. And now imagine our job is to use these two features and come up with a model. So it's a model based on these two features, x1 and x2, and it predicts, so this h of x1 and x2 predicts class, predicts some categorical variable. So imagine, for us, let's focus on an example where we're trying to predict materials as either metals. We can say, that's integer 0, for instance. We can encode it with an integer. We can say, we're also curious about predicting materials as semiconductor. So let's encode that with 1. And let's also classify materials as insulators. So let's call this 2. So we want to, for every material, classify it and sort it into one of these buckets, 0, 1, or 2. Cool. And decision trees are going to help us figure out that problem of having to come up with this model here. Great. So let's imagine we plot all of our data, and imagine we plot our training data. So with our training data, training data, we know the labels. Labels are known. So we can plot this data, and we can plot it with the labels that we know already. So that'll help us understand the problem a little bit better. So imagine, our metals, we'll use maybe a circle here. For semiconductors, we'll use a triangle to represent semiconductors, and for insulators, we'll use maybe an X. If that's not too confusing. So imagine we get, 3 materials that we knew were metals, and they show up here. They have x2 and x1 values of these respective points. Imagine we do this for 3 semiconductors. They show up over here, and insulators show up over there. Great. So now we have a 2-dimensional plot based on these 2 features, x2 and x1. And we start to see that these different material classes have, distinct groupings in space. And so let's use our tree algorithm. And I haven't told you what we're allowed to do in this algorithm, but basically trees allow us to draw in this graph vertical and horizontal lines. Horizontal lines. And what do I mean by that? Well, I mean in math terms that we can either have terms like x2 is equal to c or x1 is equal to c, where c is a constant. So that means we could, if we had lines, numbers here, maybe, this is 1, this is 1.5 here, values of x2. We could draw a line that says x2 is equal to 1.5. That would look like a line like that. Great, so this is x2 equals to 1.5. And that splits our data into 2. So now we have 2 different regions. We have this region over here. And that region is what? Well, that region is x2 is less than 1.5. So we'll call that region 1. And we have x2 is greater than 1.5. and we'll call that region 2. So if you notice from this plot, everything in region 1, everything where x2 is less than 1.5 is a metal. So that helps us. We can say, you know what, if any new data point, so let's call new data where we don't know the label, or maybe we do, but we want to predict without it. For instance, in a test data set, we'll call a new data point a square here. So imagine a new data point falls in this region 1. Well, since all of the other data points in this region are metals, we'd be inclined to say, you know what, let's make a simple rule. Anything in region 1, we will predict as a metal. So we can say for data that falls into region 1, predict metal. So that almost solves our problem, but now everything in x2 greater than 1.5 is non-metal. But we don't want just metal and non-metal. We want finer classes, insulators and semiconductors. So what if we draw another line here? You can probably see where this is going. Over here, let's imagine this is, what do we want to say, 2.5? So x2 equals to 2.5. Great, so that gives us now new regions. So now we could say, for instance, our new rules here with these two lines are x2 less than 1.5. That stays the same. That we're going to say, you know what, there's only metals in this region. Let's call this a metal. Any new data point that falls in there. Now what about the sandwich region of 1.5 less than x2 less than, what do we got here? 2.5, I said. 2.5. Let's call this a semiconductor. And the top region, so this is everything in here. Great, since we only have semiconductors in there, we'll classify it as a semiconductor. So this is another region. Maybe we call this region 1 now, and maybe this is region 2. And our last region then would be x2 greater than 2.5. And since there's only insulators there, we'll classify it as an insulator. Great, so we've actually solved our problem already just using these two simple lines. And that's the most simple tree that we can develop. Great, so we built our first tree, our first decision tree, and we only used, what did we only use? Well, we only used horizontal lines. So I told you that we can actually use vertical lines as well. And what do I mean by vertical lines? Well, horizontal were the lines x2 equals to c, but we can also use vertical lines, meaning x1 equal to c. And more generally, if we had more features, we could also say, x3 is equal to c. It could be a split. Great, so let's think about this data a little bit more, and we can think about different ways to split up this data, where each region we classify as a new data point that shows up in that region as a specific class. So what did we have? We had our metals here. Let's draw this again. We had our semiconductors as triangles, and we had our insulators over here. Okay, great. So what we did before is we made two horizontal splits here. x2 equals 1.5, x2 is equal to 2.5. And then we came up with some regions, and we were able to then classify a new data point that showed up here, for instance, as belonging to this region, and therefore it is a semiconductor. We could have also come up with different splits. Maybe we kept with our first split here, which was x2 is equal to 1.5. But we could have also then said, for a second split, let's do a split like this, which is now x1, what is that? Let's say this is x1 is equal to 2. So we have two splits. We have x2 equals to 1.5. That's our first split. And then we have a second split here where we're saying x1 is equal to 2. So now we have three regions again. So we could say, this is region 1, maybe this is region 2, and this is region 3. And we call these, these regions that we end up with after we make these splits in a tree as decision boundaries, meaning any square that shows up in region 2, we're going to classify as a semiconductor, for instance. A square, a new data point that shows up over here in region 3, we'll say this is an insulator, since most of the data points here are insulators. So that's great. How would our decision rules look now? Well, now we would say, again, same rule initially, where we say, hey, if x2 is less than 1.5, then we've got a metal. Now our other rules are a little bit more complicated. If x2 is greater than 1.5 and x1 is less than 2, this is going to be a semiconductor. And so this is this region, x2 is greater than 1.5 and x1 is less than 2 here. And you can spell out the last one for insulators. Again, it's greater than 1.5 for x2 and x1 is now greater than 2. This will be our insulator. So that's a perfectly good tree as well. Now that we have these decision rules and these boundaries, we can come up with a new structure. One that you'll start to see why we call this a decision tree. We come up with actually a tree-like structure. So we ask a question here at the top. We say, for instance, with this graph up here, we say, what is the question? The question is x2 greater than 1.5? If it is, if it's not, if the answer to this question is no, then we arrive at this bubble here, and we'll say any data that answers this question as no, we'll classify as a metal. So x2 is less than 1.5 would be here. And if the answer is yes, well, then we arrive at another question. And that question will be, is x1 greater than 2? If the answer is yes, then we're in this region, R3, and we'll say this is our insulator. And if the answer is no here, then we will arrive in our region 2, which we were classifying as semiconductor. Great. So a little bit of tree terminology. Normally we call these questions nodes here. And when we get to the bottom of the tree, these are called leaf nodes here. Leaves. So this is a leaf. This is just a node or an internal node. And the top node is called the root node. And we normally talk about the depth of the tree being the longest branch. This is a branch here. And since there's 1, 2, 3 nodes here, we would say the depth of the tree is 3. So this tree structure is not the only way we can represent our tree. We can also use a single function. And we're going to have to make use of indicator functions. So these will be like x, for instance, belonging to some region I. So this indicator function, which has as argument that x belongs to some region I, will be 1 if x belongs to this region I, and 0 if x does not belong to some region I. So that should be pretty familiar with for you. It's kind of similar to this delta function, which is 1 if x equals to 0 and 0 otherwise. And we're going to use this indicator function quite a bit in trees, so it's good to think about this and become familiar with it. So imagine we've got our function now, our model. Maybe this is f, or maybe we say h, doesn't matter. And it's a function of 2 variables, x1, x2. And let's just combine these two into some vector here. And we'll say, all right, now our model is a function of some vector. So this vector could be like this, x1 and x2 here. And we'll say it's equal to the single function. So let's write it out and then we'll explain it in a sec. So we have a sum from m equals 1 all the way to big M of the class M times this indicator function here. And this will be x bar belonging to some region M. So if you remember our decision boundaries, we had split up this 2D graph here into 3 regions. Region 1, let's say, region 2, region 3, and we had assigned classes to each of these regions. So we had said, you know, this class for region 3 is equal to an insulator. So we can say, you know, the class of region 3, so we'll use K to indicate the class. We'll say this is equal to an insulator, or if we use our encoding, we were saying insulators, we'll call them 2. The class of region 1 equals here, whoops, K of 1. Let's just say we can drop that big R of 1, and we'll say this is equal to a metal, or in our encoding, this was equal to 0, and K of 2 is equal to 1. So the class of region 2 that we were assigning to this region was a semiconductor, which is 1. Great. So let's get rid of this class here. We can actually say it's equal to a sum over M equals to 1, big M, and we'll have K of M here now. So this will be either 0, 1, or 2. That'll be our prediction, an encoding, times this indicator function. So this indicator function, again, is only 1 when this x bar belongs to this region M. So x bar can only belong to one of these regions, either region 1, either region 2, region 3. If it belongs to region 1, then this answer will just be K of 1. If it belongs to region 2, then the answer will be K of 2. So very simply, it just assigns a class label to each region. So I didn't explain yet how we come up with these. So how do we come up with our class estimates for each region? So let's open up a new frame here. What does our tree do here? Our tree model comes up with regions. So it comes up with these regions, R1, R2, R3, R4, and then it assigns classes for each region. So to understand how it assigns classes for each region, we need to understand how it actually estimates probabilities for regions and classes. So this is the probability estimate for the region M and for the class K. Class K. So this could be 0, 1, 2, for example, of metal, semiconductor, insulator. And before we only had 3 regions, so this could be R1, R2, and R3. So we counted regions starting from 1, classes from 0. Hopefully it doesn't confuse you. But we have our estimates for these probabilities. So we want to say, so a new data point, a square, shows up in region 2. So we want to say, hey, what's the probability that this data point of region 2, this is M equals to 2, for class K equals to 0. So what's the probability that this square belongs to this class 0 metal? So this is probability square, so new data point is a metal. So the tree actually comes up with estimates of these estimated probabilities. And we could also say, for this region 2, what's the probability that this new data point is an insulator? So this is prob of semiconductor. K equals 1 was a semi. And we could also do this for K equals to 2. So what we employ here is actually a frequentist approach. Frequentist approach, where we basically count all of the data points that we have in each region, and we basically answer the question, how many data points were there in each region and how many of each class. So it's a little bit hard to understand that, but let's look at an example. But actually, before we do that, let's throw down a formula, and then let's go through an example of this formula. So this is the estimated probability for region M in a class K. We have 1 over the data points in this region M, and then we sum over all of the data points belonging to this region M, and we have some indicator function where yi is equal to the class of interest. So let's look at an example here. Let's calculate this estimate for region PM equals to 3. So this is our region 3 here. And K equals to class label equals to 2. So for insulators. So how many data points do we have in this region 3? We have 3 data points, 1, 2, 3. So this is going to be 1 over 3. And then we're going to sum over all of the data points, and we're going to ask, and we're going to add a 1 to the sum if the yi's corresponding to these xi's. So these data points have some features here, and they have some y values here. So the associated y values for all of these data points is equal to 2, since they are all insulators. So they have different x bar values. They have different values of x1 and x2, since they lie on different points of this plane, but they all have the same y values. They all have the same class labels. They all are insulators. So we're going to sum 1 plus 1 plus 1, and this, plus 1. And this is going to be equal to 3 over 3, 3 over 3, or the probability that a new data point shows up in this region 3 and is an insulator. We're going to estimate that probability is equal to 1. So what are the probability that a new data point that shows up in this region 3 is of a different class? Well, you can count the number of data points that are of this different class. Semiconductor, well, we have no data points that are semiconductor, so we're just going to add 0, 0, 0 for each of the 3 data points that we have in here, and this probability is going to be equal to 0. Similarly, you can find out that the estimate for this region 3 and class label 0 is also going to be 0. So that's great. The probabilities all sum to 1, and we can do this for the other regions as well. Great, so we have this equation here that we can use to find out what our probability estimates are, and this hat above this probability is to signify that it's an estimate. It's not the true underlying probability distribution. Maybe if we sampled loads of materials, maybe, a real metal actually shows up on this side. Our estimate wouldn't be exactly true. But another way to think about this probability estimate is simply you count what fraction of class label M, fraction of data points, of data of class K, in region M. So we're basically just saying, let's look at all of the data in region M. What fraction of all of the data in region M belong to a specific class label K? And that's what we're really doing here. So, for region 3, we had all of the data in region 3 belong to this insulator class, and that's why the estimated probability was 1, and the other probabilities were 0, since they had 0 fraction there. So this makes our problem a little bit easier of how do we estimate a class for a region. We simply say which probability is biggest, which probability estimate is largest. So we maximize over the possible values of K this probability estimate K, and this gives us our estimate for the class of region M. So, for our example, we had 3 regions here, and we focused just now on one region, so a specific M, because we're trying to find the class label for a specific M. And then we say, okay, of all of the possible class labels, 0, 1, 2, which of those probabilities was the largest? And whichever one was the largest will be our new estimate for that region. So in our example, it was of region 3 if class label 2 was larger than the other ones, 3, 0, and 1. So it was larger than the class labels. Let's do this a little bit better. Let's say it was larger than the estimated probability of region 3 for class label 1, which was also equal. They were both 0 of estimated probability of region 3 and class label 0. So that means for region 3, we're going to estimate a class label of region 3 is equal to 2, or insulator, if we decode that integer. Great, so now we have a way of coming up with class labels for each region. Great, so now we know how to get our class labels from our regions by using these probabilities, estimated probabilities. We didn't yet figure out how to get these regions. So before we just did this by hand, how do we get these regions R of M? How do we split our different variables, feature variables, so that we get different regions? And to do so, we're going to need first a cost function. Cost function. So normally we call this J. Some other variables are used, maybe big L, cursive L. And the first cost function we'll look at is called the misclassification error, or misclassification rate. Misclassification, let's call it rate. And it is quite simply the number of misclassified results over total number of classified data. So maybe you're fed your tree a bunch of training data. Maybe you fed it 100 data points, and there were 3 misclassifications. Then you would say my misclassification rate is 0.03. Or maybe it was some test data, it wasn't training data, but that's how you calculate it. For us, we're going to use a little bit more interesting notation, just so you keep getting used to this. Indicator notation. We're going to say 1 over total number of data, and then we're going to sum over all of the different xi values. And then we're going to say, belonging to R of M. And we're going to sum over all of the M's, actually. So this will be a double sum. So we're going to sum over all of the regions, then sum over all of the data points in that specific region. And then we're going to have an indicator function here, where yi, when it is not equal to k of m. So we want to know the times we classified this data wrong. Because remember, k of m is our estimate for the class label for region M. So if we sum this up, we will get a number of misclassified data points. And if we divide by n, then we have the number of misclassified data over the number of classified data points. So this misclassification rate is quite useful, but it's not differentiable. So not differentiable. And our tree algorithm is actually going to be based on optimizing this cost. And so very likely we'll be taking, in all forms of doing this optimization, the fast ones will be taking derivatives and looking at which steps we should take next to find the best optimal parameters in this space. So we'll actually use a differentiable cost function. And this cost function that we'll be looking at now is called the Gini index. Gini index. So this is used also in economics, and it's a measure of inequality. For us, it will be a measure of the purity of a region. And we'll talk about how we can see that. Purity of region. So let's calculate it for one region. So let's say for M, and it will be equal to sum over the classes from k equals 1 to big K. And now we'll use our probabilities, estimated probabilities. So estimated probability for region M, class K, and then 1 minus this probability. So this looks a little bit weird unless you've ever used entropies or looked at entropic measures. If you haven't, no problem. We just need to think about what these things actually mean. So again, this is the estimated probability for region RM and for a class label K. So this is 0, 1, 2, this is 1, 2, 3. And let's calculate this for an example. So we remember our example here where we had only insulators over here. And we calculated that this estimated probability for region 3, class label 2 is the insulator encoded as an integer, was equal to 1. So let's substitute this in for our data. And we found for this region, the other class labels 3, 1 was equal to P3, 0, all equal to 0. And if we do this sum, then we will have P32, which will be, so let's write this out for a second. P32, 1 minus P32 plus P31, 1 minus P31 plus P30, 1 minus P30. So I've written this in the opposite order, so this term should actually be coming first, but since it's an addition, we can just move these around, no problem. So this is just this summed out for region M equals to, what region are we looking at? We're looking at region 3. Great, so now let's substitute these values that we have here, and we will have 1 times 1 minus 1 here, plus, what is this going to be? 0 times 1 minus 0 plus 0, 1 minus 0. So this is going to be equal to 0. 1 minus 1 is 0. 0 times anything is 0. And we end up with a Gini index. So Gini of region 3 is going to be equal to 0. And this tells us something. It tells us actually that our region is pure. Region is pure. It means there's only one type of class label in that region for our training data. And that's what we're able to see. So that's what we're really going to try and do with these splits. We're going to try and make our Ginis as close as possible to 0. So we're going to try and minimize these Ginis for all of the regions that we're looking at. And so we're going to try and make splits. So make splits to minimize the Gini of the total region that we start with. So we'll explain that in this next frame. Great, so let's go through this algorithm to train our tree. So we basically have some space here. So imagine, you know, our plot here, x1 and x2, and imagine, you know, the apparatus we were using to get data for different materials that spat out x1 and x2 values only goes up to, you know, this, maybe this region, x1 max, and maybe x2 max, and the lower bounds were both 0. So we have some region initially, and we want to know, how do we split this region? And the question we really ask is, you know, how do we minimize the Gini of this region R by making a split? Making split. So let's think about what happens when we make a split. Well, we end up with now 2 regions. So we started off with this big region R, and now imagine, you know, we make a split point on x1. So imagine, you know, this is x1 is equal to c, and now we end up with some region to the left and some region to the right. And then we can calculate, so this was, we had some initial Gini of this region R, And so this is probably going to be very impure. And we're trying to make it more pure, so minimize the Gini by making the split. So we can calculate now the Gini of this region to the left and the Gini of this region to the right. Great. And how do we do that? Well, we say this cost is now going to be the number of data points on the left over the total number of data points in region R. So in region R, we had some big N data points. Now we only have some small NL on the left region and some small NR on the right region. We multiply this by the Gini of this region to the left. And we add, of course, the number of data points to the right over the total number of data points before the split times this Gini of the region to the right. So this is a little bit confusing, but basically it says is by making this split, we now have two different regions. And now these two regions have their own purity metrics. So this region has a new Gini and this other region has its own Gini. And we want to weight these Ginis by the number of data points that showed up in this region. So we had an original n data points, and now maybe there's only 3 data points in this left region. And if there's only 3 out of 100 original data points, well then this region is not so important. So even if this region is totally pure, it's only pure for 3 data points. So we want to make splits that make as many data points as possible pure and make both regions pure. So we weight it by the fraction of data points in this region. So we want to make splits that will make both of these regions as pure as possible. Great. So we want to make this as close to 0 as possible. And we only make the split, if this j here is less than the original Gini of the total region. So we have some initial Gini here, and if the split gives us some value of j that's less than the original Gini, well then it means that we were able to make the purity of our two regions, weighted by the number of data points in those regions, purer than what we had originally. Then we should go ahead and make that split. So we'll keep making those splits until we have some stopping mechanism, or until we run out of data to split. Maybe we only have 3 data points now in this region, or 2 data points, and that could be a stopping mechanism to say, hey, tree, keep making splits that minimize this Gini, keep making this j that is less than this original Gini. So keep making splits here. Maybe we'll make another split here, maybe another split here, maybe another split here. And now, this is our region, our final region here, and maybe there's only 3 data points in here, and we'll tell our algorithm, if there's only 3 data points, don't make another split here to subdivide this region even further. Great. So again, if NL is greater than NR, well now this value is weighted more in this term. So that kind of makes sense. We're weighting by the number of data points. And now how do we come up with the splits? So we have to make a split on some feature. So some feature here. So maybe we've got multiple different features, x1, x2, x3, x4, x5, and we need some split point as well here. So this would be some split where the feature xj is equal to s. So this could be, x1 was equal to 2, for instance. We said c, but that we could say, okay, well, we can come up with what's the cost of this split. It would be j of x1, 2. Great. And we're going to look over all of the different features that we have and all of the different possible split points. So, we had maybe for our original example, 2 features here. We had many different possible split points over these 2 features. We could have drawn horizontal lines like this. We could have drawn vertical lines for this point here, maybe another vertical line here. There's no real limit here to how close we could have made these 2 split points. And we're going to basically try all of these different values and then compare what these costs are for all of the different values. And we're going to make the choice that minimizes j of xjs. So we find out what are all of these values, we come up with a matrix, and then we choose the one that minimizes this cost function. And there are algorithms that do this in a little bit smarter way to speed up this computation, but in essence what we're really trying to do is just find this split that minimizes the Gini for a region. Great, so just to recap here, we look at all of the possible split points over all of the possible features, and we choose the one that gives us the best, the smallest j here. And remember, we only make the split if this j is smaller than the Gini of the original region. So we start with this region here. Maybe we make a split here because this is the one that gives us the best j, which is smaller than g of r. And now we have two different regions here, and we act on these two regions separately. So we might split this region to the left here like that. We might split this region to the right like this. So now we have, even more regions here, and we would keep then looking at these regions again and splitting these subregions into even more subregions until we have some stopping mechanism like either the depth of the tree. So that's something we will control in the tutorial if you do the tutorial with us, or the minimum number of data points in a subregion. Great, so that wraps it up for classification. Now let's look at what trees can do for us in regression problems. So regression problems, we're trying to estimate a continuous number for the most part. So this could be, let's say, volume per atom. And this volume per atom could take values from 0 all the way up to infinity. So this is, I think, an open bracket. Hopefully mathematicians don't kill me for that one. And now we're going to do pretty much the same thing. We're going to really look at this problem and, imagine we just have one variable here. Let's say this is, what do we want to call it? Let's say this is some variable, doesn't matter what it is. We can call it x1. And this is the value, the target that we're trying to predict. And imagine we get some data like this. So this time, all of the data is just dots. We don't have classes. And we've got some function that looks like this. So this kind of looks like it belongs to some step function class. And what we're going to do in a regression tree is we're going to make splits again. So we're going to make some type of split like this. So let's even just draw the split. So this would be x1 is equal to some constant. Maybe we say it's 2. And then for each region, so we have some region to the left of the split, some region to the right, we're going to estimate a constant. So we're going to say there's some constant of this region to the right. There's some constant of this region to the left. And what do we make as our constant estimate? Well, we're going to find out that it's actually going to be the average of the y values when the x i's belong to this region R. And so what do I mean by xi and yi? Well, we have pairs of data points here. So for us, I actually call this x1. So this will be x1i and yi. So it's two subscripts, sorry about that. But we have rows of data. So this is one column of data, and we have our target column of data. So, imagine this data point here. What will that value be? That'll be, x1 equal to, let's say, 0.5. And what is the y value? Well, it is y equal to 2. So that'll be one data point, and the others will also have values here. And so we're going to take the average in this region of all of the data points in this region. So we're going to say all of the yi's where the corresponding xi's belong to this region. Great. So you could just say, this is the average of the yi's in that region. And this is, again, this average of the yi's, but this is now belongs to this region L. So we'll actually prove why we choose these constants to be the averages in the tutorial introduction video. We don't have time now, but what we do with trees is we constrain ourselves to only choose constants. So more advanced algorithms, instead of choosing a constant here, which will be the average, so it'll look like this. It'll be some constant, y equals to 2, for instance. That'll be the constant of this region L. You could also estimate, a line, for instance. That could be a more advanced algorithm. And what you see with this model is it's piecewise constant. Piecewise constant. So we've constrained our model to be constant in these different regions. So if we didn't constrain it to be constant, it would just be a piecewise model. It could be, piecewise linear. There could be another linear point here, maybe another here if we had another split, but it's piecewise constant. So that means, if we have some parabola here, our splits will split this data so that we have different split points here, and each region will be estimated by a constant. So this will be a split point, 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 this will be a split point. And for each of these regions, or i's, for instance, we're estimating our function f of this, any data point that ends up in Ri, to be some constant of this Ri. Okay, so we have this piecewise constant function, and we can represent it with a single function again. We can have some f of xi. So some data point shows up, and we will say, we don't even need this xi here. Sorry, f of x. Let's imagine there's just one variable, doesn't have to be. And we look over all of our regions. So maybe we have big M regions, and we have this C of this region M. So I'm saying C of M is equal to the constant of that region M. Each region here is estimated by some different constant, and a constant, remember, here is this horizontal line. And then we have to multiply this by an indicator function. So hopefully you're getting used to these guys. And the indicator function will be, does the x belong to one of those region m's? Great. And we could turn this into a vector to say, maybe we have multiple columns of input data, multiple features here. And we say, does this data point belong to this region 3? If it does, then this function, this indicator function, is 1. If not, it's 0. So it can only be true for 1. So let's say x bar belongs to region 3. Then this function will be equal to c of 3. It'll be equal to this constant that we're estimating all values that fall in this region as being equal to this constant. So that's great. What about our cost function now for regression? Well, normally we use the mean squared error, or the sum of squares. So sum of squared errors will be equal to sum over I equals 1 to all of the data points, so over n data points, and we'll have the true targets minus our estimate for these targets. And we'll square this. So to take the mean squared error, we'd actually have to average this. So this is the sum of squared errors. Great. And optimizing this is the same as optimizing the mean squared error. And so we told you that we can input our function that we found already, that single function from this page back here. And we can look at finding what is the best split. So if you watch the tutorial, you'll find out again why we choose the CMs to be the average y value of that region. And so imagine now we have some region R, and we want to make a split. So we end up, with this left region, with this right region for some x here. And what we want to do is take some minimization. So we want to find the feature that we should split on. So much like the same tactic as with classification, we're going to try all of the features, try all of the possible split points, and minimize over all of them. Keep track of the good ones, maybe explore the good ones a little bit more in deeper detail. And then we're going to try and find, the minimum constant for this left region. So imagine this is region 1, this is region 2 here. region 1, region 2. And this will be some sum over all of the xi data belonging to region 1. And now we can find, well, what is the squared error for this region 1? Well, it's yi's minus all of the data that show up in this data, all of the data points that show up in this region 1, we're going to estimate with this constant, C1. It's the constant that we're estimating for this region. And now we're going to also add, and we're going to minimize to find the C2. And sum over all of the xi's that belong to this region 2, and the same deal here. We're going to find these squared errors. So we've estimated all of these yi's in this region 2 are equal to this constant, and there's going to be some error there. So we're going to try all of the features, all of the possible split points, and then we're going to also find the minimum C1 and C2. And in this video, we didn't explain how to come up with these constant estimates, but in the tutorial for decision trees, we actually prove that these constants need to be the average of the y's in that corresponding region. So they have, the yi's have corresponding xi's that belong to this region. So this is the average y in this region M. And that will be the constant that minimizes the mean squared error in this term. Great, so let's take a 5-minute break for a question.